Space has always had this reputation for being the ultimate nothing. You point at the night sky, stare into the dark, silent infinity above you, and your brain goes, yep, zero, nada, a whole lot of cosmic empty. And honestly, who could blame anyone for thinking that? Human eyes are not exactly built with the cosmic equivalent of night vision goggles, so from where we stand, everything between the stars looks about as eventful as a black sheet of paper. But the funny thing, the surprising thing, is that the universe is an absolutely terrible minimalist. It talks a big game about being empty, but secretly, it is the kind of place that would hide mismatched socks, old receipts, and 3-month-old snacks under the couch if it had one. Space is not a void. It is a soup. A weird soup. A soup made of ingredients you cannot see but that absolutely refuse to leave. Good evening, curious minds. I truly hope you will enjoy today's video. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift towards sleep, consider subscribing, but only if you enjoy these calm journeys through the universe. Now, let's begin. The real twist, though, is that space only appears empty because it stretches our sense of scale until it snaps. Imagine you are standing in a field and someone spreads a handful of dust across a mile of land. If you searched for it grain by grain, you would swear there was nothing there. But zoom in with the right tools, and suddenly that grain of dust becomes the star of the show. Space works the same way, except the distances are so large and the stuff in it is so incredibly spread out that even the most determined detective would struggle to prove there is anything there at all. Yet every cubic meter of space contains traces of something. Atoms drifting like cosmic wanderers, particles zipping around like they are late for an appointment, and energies humming quietly in the background, like a refrigerator you forget is running until it annoys you at 3 in the morning. When people hear that space is full of stuff, they sometimes imagine chunky debris fields and floating boulders like every science fiction movie ever. But no, the truth is far stranger and far more delicate. The ingredients that fill space are so tiny and so spread apart that if you scooped up a room-sized volume from the middle of deep space, you might find a few lonely atoms looking like they forgot where the rest of their friends went. But those stray atoms matter. They matter because on the grand scale of galaxies and cosmic evolution, they shape everything. They drift, gather, and someday help build stars, planets, and everything that eventually wonders about its origins while eating breakfast cereal. The universe also has this habit of leaving behind traces of phenomena that were once unimaginably powerful, but are now nothing more than faint whispers drifting through eternity. These whispers travel through every corner of the cosmos, brushing past galaxies, slipping through solar systems, and gliding right past Earth without so much as slowing down. And we do not see them, we do not feel them, but they are there. They make space more crowded than it looks, crowded not with objects but with stories. Every empty patch of sky is basically a storage locker that the universe forgot it rented. If you could stand in deep space, really stand, ignoring all the inconvenient details like no air and your body freezing faster than your hopes on a Monday morning, you would still be surrounded by countless invisible travelers. Tiny particles would drift past like cosmic tumbleweeds. Radiations from distant stars would wash over you, and energy fields would hum faintly, as if the universe were practicing its scales. Even the so-called vacuum of space trembles with activity at the smallest levels imaginable, because nothingness, true nothingness, is something the universe apparently decided was too boring. It is wild when you think about it. Here we are, living in a cosmos that pretends to be empty, the way a teenager pretends their room is clean. They just shove everything where you cannot see it. Space is very committed to its aesthetic of emptiness. It wears black, stays quiet, and spreads everything out so far you could trip over the same particle twice, only if you were extremely patient. But underneath that sleek, minimalist appearance is a constant buzzing fullness, particles, energies, whispers of ancient events, and hints of future structures waiting to form. And that is really the hook, the idea that space, despite looking like nothing, is bursting with invisible activity. It is not a blank void. It is a canvas splashed with the faintest strokes of matter and energy, so thin your eyes never catch them, but so essential the universe would fall apart without them. So next time you stare into the night sky and feel the quiet of it settle over you, remember this: space may look like the universe finally cleaned its room, but really, it just shoved everything deep under the cosmic bed and hopes no one checks. If you were to scoop up a handful of interstellar dust, you would not feel anything at all. Not a tickle, not a whisper of friction, not even the smug satisfaction of holding cosmic material older than your entire species. Interstellar dust is made of particles so tiny that calling them grains is almost an exaggeration, more like the crumbs of crumbs left behind when the universe bites into a star. Yet these microscopic flecks drift through the gaps between suns, and despite being as small as they are, they play roles so dramatic they might as well demand their own backstage dressing rooms. Space, it turns out, has worse dust issues than an abandoned attic, and that dust is constantly rewriting the shape and color of galaxies. Interstellar dust does not form in some tidy, predictable workshop. It is born in violence, the kind of cosmic chaos that would make a demolition site look like a quiet afternoon at a library. When a star reaches the end of its life, it swells, shivers, and coughs out layers of its own material. Some stars throw gentle breezes of carbon-rich soot into their surroundings, like they are exhaling smoke rings into the galaxy. Others explode with such force that the debris is flung across space at speeds that would make even the wildest roller coaster lose confidence. From these endings, tiny solids emerge, bits of iron, slivers of carbon, frozen droplets of oxygen and silicon that clump together as they cool. They start as chaos and drift into elegance. Once freed into the galaxy, these particles take on the personalities of wandering nomads. They drift through light years of space with a patience that only the cosmos could maintain. In human terms, a single dust grain can take millions of years to cross a single light year. It is the slowest road trip imaginable, but these particles are not in a hurry. They glide between stars, absorbing stray photons, occasionally bumping into other particles, and slowly accumulating thin layers of material around themselves. Some gather icy mantles, like glass beads wearing winter coats. Others soak up organic molecules, becoming the seeds for future chemistry. They are small, yes, but they are persistent. And persistence in the universe is powerful. One of the most surprising things about interstellar dust is how much it changes the light that passes through it. When starlight hits these grains, the dust decides to act like a moody filter. It dims some colors, scatters others, and stretches the glow of distant stars so that they appear redder than they actually are. Astronomers have spent decades untangling this photonic mischief, figuring out how dust hides the true brightness of stars, how it masks enormous clouds of gas, and how it tricks telescopes into seeing shadows where there are none. If the universe ever held a masquerade ball, interstellar dust would be the one handing out the masks. But dust is not just a cosmic prankster. It is also a builder. Over time, dust gathers into large, cold clouds that float silently through the galaxy. They are dark, dense, and so well hidden that many of them remain invisible even to sophisticated instruments. Inside these clouds, dust helps cool the surrounding gas, allowing atoms to move slowly enough that gravity can finally take charge. Eventually, these regions begin to collapse, not in a dramatic end-of-the-world kind of way, but in a slow inward drift that takes its sweet time. As the cloud contracts, clumps form. As clumps form, heat rises, and when everything gets just dense enough, stars are born. Dust, while small and easily ignored, is absolutely essential to star formation. It is the cosmic version of that quiet person in the group project who ends up doing half the work. Interstellar dust also carries the early ingredients of planets, the building blocks of rock, metal, ice, and even complex molecules hitch rides on these specks as they swirl around young stars. In protoplanetary disks, the spinning plates of material that surround infant suns, dust grains collide, stick, combine, and grow. Slowly, they become pebbles. Pebbles become boulders. Boulders become planetesimals, and those become planets. Every world you have ever heard of, including the one you are sitting on right now, owes its existence to dust so tiny you could fit billions of grains on your fingertip. The grand landscapes of mountains, deserts, oceans, and cities all trace their lineage back to fleeting particles drifting through ancient space. What makes these grains even more fascinating is how long they can survive. Some drift through the galaxy for billions of years, carrying memories of stars that died before Earth existed. They wander like cosmic elders, outliving the objects that created them and influencing objects that will come long after. They absorb radiation from supernovas. They witness the slow rotation of spiral arms. They slip between hydrogen clouds and skirt the edges of nebulae. If dust could talk, it would have stories no civilization could fully comprehend. So the next time someone looks at space and says it is empty, imagine a vast cosmic attic filled with forgotten specks that quietly shape the destiny of stars and planets. They are tiny, almost invisible, and sometimes inconvenient, but without them the universe would be unrecognizably barren. Space might look dark and quiet, but it is filled with the smallest of storytellers, drifting silently between the stars. When most people imagine the regions between stars, they think of a kind of cosmic desert, vast, dry, empty, and silent, the sort of place you would only visit if every other destination in the universe had a "closed for eternity" sign. But the truth is far stranger and far more elegant. The space between stars is filled with enormous clouds of gas so thin they make the air on top of Mount Everest look like soup, yet so massive that they can stretch for tens, hundreds, even thousands of light years. Space may look like an abyss carved out of nothingness, but even its most abandoned corners have more gas than a family road trip after everyone eats questionable burritos. This gas is delicate, ghostly, nearly invisible, and shockingly powerful in the role it plays across the galaxy. Hydrogen, the simplest element in the universe, is the main player here. It floats between stars like a silent sea, spreading out so thinly that in many regions there are only a handful of atoms in the volume of a large living room. Imagine looking for a single grain of sand in an Olympic-sized swimming pool. Now take the sand away. That is how subtle interstellar hydrogen is. And yet, despite being nearly undetectable to ordinary senses, this gas forms the backbone of galactic architecture. The Milky Way, that grand spiral we call home, is shaped not just by shining stars, but by these enormous drifting oceans of hydrogen. The beauty of this gas is in its range of personalities. Sometimes it spreads out thinly, a warm and peaceful cloud that glows faintly in the soft ultraviolet light of nearby stars. Other times it thickens, still incredibly diffuse by human standards, into cold, dense pockets where temperatures drop to levels so low they make deep space look tropical. In these cold regions, hydrogen atoms pair off into hydrogen molecules, forming a more complex dance that influences how the cloud bends and swirls. These molecular areas are the birthplaces of future cosmic drama, but even in their quiet state, they are sprawling structures stretching across the galaxy like whispers woven into the darkness. If you could float inside one of these hydrogen clouds, you would not see anything. Not a shimmer, not a fog, not a vapor. It would feel like floating in nothing. But the gas would be there, passing through you, brushing against you in quantities so small you might only encounter one or two atoms in the time it takes to yawn. Yet, on the scale of millions or billions of years, these atoms matter tremendously. They gather, drift, collide oh so gently, and slowly sculpt the global outline of the galaxy. Space might feel empty in the moment, but given enough time, even the faintest cloud can build the next chapter of cosmic evolution. One of the most extraordinary things these hydrogen clouds do is shape the grand spiral arms we see in many galaxies. The spiral arms are not just rows of stars arranged in photogenic patterns. They are density waves, massive, slow-moving compression zones that sweep through the galactic disk. As the wave passes through, hydrogen gas is gently squeezed, like air being pushed ahead of a slow-moving train. This compression causes the gas to clump, which changes its temperature, which then changes its movement, which then changes the layout of the entire region. Even though these clouds are delicate beyond belief, their enormous scale allows them to form a scaffolding for the galaxy, guiding the positions of stars and marking out the spiral arms like glowing trails. But it is not just the spiral shape that hydrogen gas helps maintain. It also forms vast emission nebulae, giant glowing clouds that shine because they are energized by nearby young stars. When high-energy ultraviolet light hits hydrogen, the gas gets excited, and when it calms down again, it releases soft, colorful light. The result is a luminous cloud that can stretch across dozens of light years, glowing like a cosmic lantern drifting through the galaxy. These nebulae can be smooth or turbulent, quiet or chaotic, shaped by waves of pressure from stellar winds or shock waves from ancient explosions. Even more delicate are the neutral hydrogen regions, which do not glow at all. These are detected through an incredibly faint radio signal emitted when the electrons in hydrogen atoms flip their orientation relative to their protons. This spin flip transition happens rarely. An atom may wait millions of years before doing it, but when multiplied across the vastness of space, the signal becomes a faint but detectable whisper across the galaxy. Through these whispers, astronomers map the Milky Way's hidden structure, tracing flowing streams of gas, mapping twisting filaments, and revealing rivers of hydrogen that bridge the spaces between spiral arms. What is remarkable is how much movement hides in this quiet, nearly invisible medium. Hydrogen clouds drift through the galaxy on enormous orbits. They collide gently, pass through each other like ghosts, and spread out again. They are influenced by magnetic fields, nudged by gravity, and stirred by the motions of stars. The environment may seem still, but over cosmic timescales the gas swirls and folds like slow-motion smoke from a candle. So while space may look like the universe forgot to furnish most of its living room, the truth is that those seemingly empty spaces are filled with delicate, sprawling seas of hydrogen gas. They do not shout for attention. They do not shine unless coaxed. But they shape galaxies, guide their evolution, and quietly thread the universe together. In the dark between stars, hydrogen waits, thin, patient, and endlessly important. If the universe has a mischievous streak, and let us be honest, it absolutely does, its favorite prank has to be cosmic rays. These things are like the cosmic equivalent of invisible darts launched across unimaginable distances with no warning, no noise, and no intention other than barreling into whatever happens to be in the way. They may be called rays, but the name is misleading. They are not gentle beams of light drifting peacefully through space. Cosmic rays are actually particles, individual bullets of matter traveling at speed so close to the speed of light that they make even the boldest science fiction seem timid. They zip through the galaxy with a kind of reckless enthusiasm, as though the universe decided the laws of physics were too quiet and deserved a little chaos. Cosmic rays come from origins so energetic they make ordinary stars look like flickering candles. Some are born in the explosive deaths of massive stars, where conditions are so violent that atoms get ripped apart and flung outward in all directions. Others emerge from jets fired by supermassive objects like black holes, which spit out streams of particles with a kind of cosmic impatience. And then there are the truly mysterious ones, the high-energy cosmic rays whose origins are still unknown, arriving at Earth like unwanted packages with no return address. They are a reminder that the universe still loves to keep secrets, even after billions of years of practice. What makes cosmic rays incredible is not just their origin story, but the sheer amount of energy packed into their tiny forms. A single high-energy particle can carry more punch than a baseball thrown by a professional athlete, except this baseball is smaller than an atom and traveling at nearly the speed of light. If humans could harness even a fraction of that energy safely, our power problems would be solved. Our engines would be efficient beyond imagination, and our science fiction dreams of interstellar propulsion might not remain fiction for long. But cosmic rays are not here to be helpful. They prefer to stay wild, unpredictable, and ready to smack into anything that crosses their path. When they arrive at Earth, cosmic rays do not politely knock. They smash into the atmosphere, colliding with molecules of nitrogen and oxygen like tiny battering rams. The impact is so energetic that it triggers a cascade, an entire shower of secondary particles raining downward through the air. Far above the ground, this storm is invisible. It passes through you without you noticing, like a ghost that refuses to acknowledge personal space. And yet, without these interactions, we would never know cosmic rays existed. We detect them through the faint flashes, ion trails and particle showers they create, the same way you might detect a stranger's footsteps by the ripples they leave on a pond. Cosmic rays do more than just pepper Earth's atmosphere. They travel through the entire galaxy, threading through star systems, brushing past planets, and slipping through magnetic fields as if testing their strength. In some regions, magnetic fields catch and redirect them, sending them spiraling along galactic arms or funneling them into looping paths. In others, the rays slice straight through, unaffected and unstoppable. They bring with them hints of their origins, tiny signatures of the environments that accelerated them. The mix of particles they carry tells stories of nuclear fusion, ancient explosions, and extreme magnetic storms. One of the strangest qualities of cosmic rays is their persistence. A particle launched from a distant supernova might travel for millions of years before it ever collides with something. It may pass by countless worlds, glide through nebulae, and skim the edges of star clusters. It does all of this without slowing down, without aging, and without knowing where it will eventually end up. If cosmic rays had personalities, they would be the ultimate wanderers, restless travelers who never stop moving and rarely leave souvenirs behind. Even stranger, cosmic rays are partly responsible for maintaining a kind of delicate balance in the galaxy. They ionize gas clouds, influencing their chemistry and sometimes triggering reactions that would not happen otherwise. They can affect the charges in planetary atmospheres, shaping weather patterns in ways scientists are still studying. And deep underground, they leave faint tracks inside minerals, like tiny signatures that can be read billions of years later. You would never guess that something so small and so uncontrollable could leave such a long-lasting mark. But cosmic rays do not care about expectations. They care about momentum, energy, and moving forward at all costs. The joke, of course, is that cosmic rays are the universe's way of throwing invisible darts at everything. They zip around with no aim, no agenda, and no warning. You cannot dodge them. You cannot hide from them. They pass through worlds, machines, forests, oceans, and living things without slowing down. They are everywhere and nowhere, unpredictable and unstoppable. And while they may be the universe's oddest version of target practice, they also serve as reminders that space is alive with motion, energy, and stories written in particles so small we barely notice them. Cosmic rays are not the quiet emptiness we imagine when we stare into the night sky. They are the buzzing, restless heartbeat of a universe that prefers action over silence, chaos over stillness, and curiosity over calm. If you could shrink yourself down, not just to the size of an atom or even smaller than a proton, but far beyond anything we normally call small, you would eventually reach a strange layer of reality where the universe stops behaving like a place and starts behaving like a performance. At this unimaginably tiny scale, everything you think of as solid or empty dissolves into a restless sea of activity. Fields stretch across every corner of existence, layered on top of one another, woven together like invisible threads in a cosmic tapestry. These quantum fields are not polite or quiet. They do not rest, settle, or sit still. They shimmer, quiver, flicker, and pulse, even in total darkness, even in what we casually call empty space. Those fields hum with energy as if the universe had one too many cups of cosmic coffee and now cannot stop vibrating. Quantum fields are the strange rulebook underlying every particle in the universe. Instead of particles being little beads that drift around like cosmic marbles, each particle is actually a tiny blip, an excitation of a field that exists everywhere. There is a field for electrons, a field for quarks, a field for photons, and so on. These fields are universal. They fill all of space, no gaps, no exceptions. If the universe were a song, the fields would be the constant background hum that lets instruments appear whenever someone plucks a string. And particles? They are the notes that rise from the hum, brief spikes of energy that appear, interact, and fade back into the vibrating sea. What makes these fields so mesmerizing is that they are never, ever still. Even when they are sitting at their lowest energy state, what physicists call the vacuum, they fluctuate. They cannot stop. They are required to vibrate by the very laws of quantum mechanics. That constant motion is not a side effect. It is the natural state of everything. The fields jiggle because the universe simply does not allow perfect stillness. It is like the cosmos has an unbreakable rule that silence must always be filled with a soft, underlying buzz. At the quantum scale, calm is an illusion. These vibrations matter. They are not just background noise. The fluctuations of quantum fields influence everything from the stability of atoms to the behavior of light. They cause tiny, momentary changes in energy that ripple through space. They push charged particles ever so slightly, nudge the orbits of electrons, and shift the paths of photons. Without these vibrations, matter would be boring and unrecognizable. Every atom in your body depends on the restless shiver of quantum fields to hold itself together. The coffee joke is funny, but the truth beneath it is mind-bending. Empty space is busy, energetic, and constantly in motion, even when nothing seems to be happening. One of the strangest consequences of these fields is that they can create pairs of particles that appear out of nowhere, not stable particles, not ones that hang around and ask for a forwarding address, just brief flickers. They pop into existence. Notice that their very presence violates the cosmic accounting books, and then promptly annihilate each other and vanish again. These events happen constantly, everywhere, all the time. They are the universe's equivalent of spontaneous hiccups, harmless but impossible to ignore once you know they exist. And they are not optional. They arise because the rules that govern quantum fields demand it. The fields also interact with each other, overlapping and influencing one another, like vibrations blending in a crowded room. The electron field responds to the electromagnetic field. The quark field interacts with the strong nuclear field. Everything is connected not through physical strings or wires, but through relationships that ripple across space and time. When we see a particle collide with another particle, what we are really watching is two field excitations nudging and pushing each other like waves crossing on a pond. What makes these fields even more astonishing is that their energy is not uniform throughout the universe. In some regions, the fields settle into a different state, creating environments where new behaviors emerge. The early universe, for example, was a wild storm of field activity with transitions that shaped the very fabric of reality. Entire categories of matter and forces emerged because quantum fields shifted from one energetic landscape to another. It is as if the cosmos updated its own operating system, and everything we know today is the result of those ancient upgrades. Even the concept of mass, what makes objects heavy, comes from the way particles interact with one particular quantum field. This field resists the motion of particles in a way that gives them inertia. Without this field, every particle would zip around at the speed of light, unable to form atoms, planets, or people. The weight you feel on your feet is, at its deepest level, a conversation between the particles in your body and an all-pervasive field humming around you. Mass is not a built-in feature of matter. It is a side effect of constant interaction with an invisible background. All of this means that when you gaze into what looks like empty darkness, You are not seeing emptiness at all. You are looking at a stage filled with invisible performers, each vibrating, shifting, and flickering with energy that never fully disappears. The quiet void between stars is alive with subtle motion, intricate patterns, and ceaseless fluctuations. It is not nothing. It is a restless ocean of something deeper than matter itself. So yes, the universe absolutely looks like it drank too much coffee, but only because the laws of nature make stillness impossible. In the quantum world, every point in space hums with a subtle, unstoppable tremor, and those vibrations, tiny and fleeting though they are the foundations on which everything else stands. If you could somehow watch the fabric of reality at its tiniest, most jittery level, you would witness a spectacle that makes even the busiest city intersection look calm. Space, even at its most empty, runs a non-stop magic show. One moment nothing, the next moment bam, something, and then a blink later, nothing again. These fleeting somethings are virtual particles, brief, flickering disturbances in the quantum fields that govern the universe. They behave like shy party guests who appear, panic, and disappear again before anyone can offer them snacks or ask them what they do for a living. Virtual particles are not like the solid, countable particles that make up matter or light. They are more like temporary ripples, short-lived distortions that bubble up from the restless depths of quantum fields. They pop into being because the quantum rules that underlie reality allow small, momentary violations of energy balance, tiny loans from the universe's energy budget that must be paid back almost instantly. These particles cannot stick around long enough to cause trouble. They surface, shiver, and vanish before the cosmic accountant notices the discrepancy. But in the instant they exist, they influence the world in subtle, surprising ways. One of the most fascinating things about virtual particles is how they arise everywhere, without exception. They appear in deep space, inside atoms, in magnetic fields, around black holes, and even in the quiet space between your neurons. If you had a microscope capable of observing quantum events directly, a tool so precise that it makes the idea of a microscope almost insulting, you would see a blizzard of tiny flickering forms popping in and out of your field of view. They would appear so quickly and disappear so unpredictably that your eyes would never catch a single complete appearance. To human senses, they are impossible to detect, but to physics, they are essential. Despite their shy, fleeting existence, virtual particles leave fingerprints everywhere. One of their most famous signatures is in the tiny shifts in an electron's behavior. When an electron sits around minding its own business, a cloud of virtual particles spontaneously surrounds it, forming a kind of entourage. Virtual pairs materialize and vanish so fast they almost do not count as existing, but while they are present, they affect the electron's electrical field. They tug on it, push on it, tweak it. The electron ends up acting slightly differently than it would if these flickering companions were not around. Even though the particles live short, frantic lives, their influence is permanent. These particles also help mediate the forces of nature. When two charged particles repel each other, for example, This can be described in terms of virtual particles, flitting back and forth between them like tiny messengers. The particles do not survive long enough to be real, measured entities, but their presence makes the interaction possible. They are like the busiest employees in the universe, except they never clock in, never clock out, and never officially exist. They show up, do their job at incredible speed, and vanish before anyone can file paperwork. Virtual particles also appear in pairs, usually a particle and its corresponding antiparticle. These pairs rise up from the quantum vacuum as if testing the waters. For the brief moment they exist, they can influence real particles, bend fields, and shift energies. Then, unable to sustain themselves, they annihilate each other and return to the vacuum from which they came. It is like watching two ghosts meet, exchange a nervous hello, and fade away with equal awkwardness. One of the strangest effects these particles create is known as vacuum polarization. When a strong electric field appears, it tugs at the virtual particles in the vacuum, pulling pairs apart just a bit before they recombine. This subtle stretching influences the strength of the field, almost as if the vacuum itself steps in to dampen or amplify the effect. Empty space behaves like a medium, not a void, dynamic, responsive, full of potential activity. Virtual particles make emptiness behave like a material, thin as it may be. Their influence becomes even stranger near extremely dense or energetic regions, such as near black holes. In those environments, the gravitational field is so intense that it can separate virtual particle pairs before they annihilate. One particle falls past the event horizon, doomed to vanish forever. The other escapes and becomes real. This strange one-way ticket system is at the core of Hawking radiation, one of the universe's most bizarre and elegant tricks. Black holes, the ultimate absorbers of everything, slowly leak energy because of particles that technically should not exist in the first place. Now, virtual particles may sound like the most chaotic guests in the quantum party, but they do follow rules, just not rules that make sense to everyday intuition. They cannot stick around long. They cannot be directly observed. They borrow energy and must pay it back quickly. But while they are here, they influence fields, tweak forces, shift energy levels, and alter the behavior of matter in tiny but important ways. Every stable atom, every predictable orbit, every reliable chemical reaction is quietly shaped by their jittery dance beneath the surface. It is tempting to picture virtual particles as little creatures with personalities, hopping in and out of existence like anxious party attendees, uncertain about their invitation. But really, they are expressions of the universe's restless nature, a sign that everything, even what we call nothing, is alive with potential. The vacuum is not a silent stage. It is a churning, bubbling cauldron of momentary activity, full of shy performers who never step fully into the spotlight. They may never stay long enough to leave a trace you can measure directly, but their fleeting presence is felt everywhere. Empty space is not empty at all. It is a continuous dance of ghost-like figures, flickering into existence just long enough to prove that quiet does not equal stillness. In the quantum world, even the shyest guests leave an impression. If the universe held a massive cosmic reunion and every type of matter showed up, dark matter would be the quiet guest, leaning against the wall, offering no eye contact, avoiding group photos, and somehow still being responsible for holding the entire party together. It is the ultimate cosmic introvert, everywhere, essential, and absolutely refusing to be seen. Unlike regular matter, the atoms that build stars, planets, people, pizza, and everything else that makes our existence interesting, dark matter plays by rules so secretive that no one has ever caught it glowing, reflecting, absorbing, or even politely interacting with light. If it had a hobby, it would be staying invisible for billions of years straight. But despite being the universe's best at hiding, dark matter leaves clues, not visual clues, because that would be far too easy. Instead, it reveals itself through gravity, an invisible tug felt across galaxies. When astronomers mapped how stars move inside galaxies, they noticed something strange. The stars on the outer edges were orbiting far too fast. Based on all the visible material, stars, gas, dust, nebulae, there simply was not enough mass to produce the gravity needed to hold those galaxies together. By all normal logic, the stars should have been flung out into the void like cosmic debris escaping a slingshot. But they stayed in place. They moved quickly, confidently, as though anchored by something massive and unseen. That something is the quiet giant we call dark matter. It does not shine. It does not glow. It does not interact with light at all. But it exerts gravity, and it exerts a lot of it. It forms gigantic halos around galaxies, vast spherical cocoons of invisible mass that cradle everything inside. These halos can stretch far beyond the visible edge of a galaxy, shaping its rotation, stabilizing its spiral arms, and making sure its stars stay where they belong. Without dark matter's steady gravitational hand, galaxies would be chaotic, unstable, and prone to tearing themselves apart. Instead, they hold together with a grace that only becomes possible when an unseen structure supports them. Dark matter does not gather in neat clumps the way regular matter does. It forms enormous, diffuse structures, shaping the cosmic web, the vast network of filaments and nodes where galaxies cluster. Imagine an enormous three-dimensional spider web stretching across the universe, except the web is completely invisible and made of mass instead of silk. Regular matter settles into this web like dewdrops, collecting where the dark matter filaments are densest. Galaxies form along these invisible threads, lining up like beads on cosmic strings. Entire clusters of galaxies, the largest structures in the universe, owe their positions to dark matter's gentle but persistent pull. What makes dark matter so fascinating is how consistent it is. It does not crash into things. It does not interact with electromagnetic forces. It does not clump into stars or planets. It simply exists as a quiet background mass, shaping the universe from the shadows. The best models we have show that there is far more dark matter than normal matter, several times more. If the universe were a pie, The slice representing visible matter would be embarrassingly thin, the kind of slice that makes you wonder why you even bothered ordering dessert. Dark matter, meanwhile, would take up a hearty, substantial portion, even though you cannot taste it, see it, or photograph it. Scientists have spent decades trying to identify what dark matter is actually made of. There are theories, hypothetical particles that might explain its strange behavior, but nothing has been confirmed. It could be something completely new, something beyond the particles that make up atoms. It might be composed of particles that barely interact with the universe except through gravity, or perhaps it is something even more exotic. Something that forces us to rethink the entire structure of reality. Whatever it is, dark matter continues to behave with the same level of commitment to invisibility that an introvert shows when someone suggests a surprise birthday party. The search for dark matter has led to experiments deep underground, where enormous detectors wait patiently for the tiniest hint of a collision between dark matter and regular matter. The detectors are shielded from cosmic rays, background radiation, and every noisy particle that could interfere. They sit in silence, waiting for one quiet tap from a particle that refuses to be observed. If dark matter were a detective story character, it would be the mysterious stranger who never appears in the same scene as the clues, but still manages to be behind everything. Dark matter also played a crucial role in the early universe. After the big cosmic expansion, the universe was a hot, glowing soup of particles. Regular matter clumped slowly because radiation pushed against it. Dark matter, however, was unaffected by light and began gathering first, forming gravitational wells that ordinary matter later fell into. These dark matter wells became the seeds of galaxies. In a very real sense, dark matter built the cosmic neighborhood long before stars ever lit up. It shaped the structure of everything that followed, guiding the formation of galaxies like an invisible architect, with a lot of patience and absolutely no desire for recognition. The irony is that dark matter, despite being one of the most influential components of the universe, will never catch your eye. You could stare into the deepest region of space and never see a hint of it, but its presence is undeniable. Every galaxy rotation curve, every gravitational lensing arc, every cluster formation map whispers its name. Quietly, of course. Dark matter would not have it any other way. It is the universe's introvert, everywhere, essential, and refusing to be seen, shaping the cosmos with a subtle certainty that reminds us that sometimes what you cannot see is doing the most work of all. If dark matter is the universe's quiet architect, then dark energy is its enthusiastic real estate developer, the one who keeps insisting there is always room for expansion, even when everyone else is begging to slow down. Dark energy is the force responsible for pushing the entire cosmos outward, with such determination that space is expanding faster than a rumor in a small town. You know the kind. Someone sneezes on a Tuesday morning, and by lunch the entire community has invented 3 possible causes, 2 exaggerated consequences, and a conspiracy theory. That is how quickly space stretches, except with fewer sneezes and more cosmic bewilderment. The idea that the universe is expanding is not new. Astronomers have known for a long time that galaxies are drifting apart, carried by the stretching fabric of space itself. But for many decades, scientists assumed this expansion was slowing down. After all, gravity pulls everything together, and with all the matter in the cosmos, stars, planets, gas clouds, and those enormous halos of dark matter, it seemed logical that the expansion would gradually pump the brakes. But the universe had other plans. In the late 1990s, astronomers studying distant exploding stars discovered something astonishing. The expansion was not slowing down at all. It was speeding up. This discovery was so unexpected that the scientific community briefly wondered if their data had misbehaved, or if the universe had played a prank involving cosmic measurement errors. But repeated studies confirmed the same thing. Galaxies far away from us were accelerating outward faster than anyone had predicted. To explain this surprising cosmic enthusiasm, scientists propose the idea of dark energy, an unseen force permeating space that pushes everything apart. Not a wind, not a particle stream, not an invisible substance, but a property of space itself, something that makes empty regions stretch on their own. The wild thing about dark energy is that it does not behave like anything familiar. Regular matter attracts. Dark matter attracts. Gravity loves to pull. But dark energy pushes. It acts like an anti-gravity pressure, gently but persistently encouraging the universe to grow. And unlike matter, dark energy does not thin out as the universe expands. Instead, more space simply means more room for dark energy to exist, which means even more pushing. It is the ultimate feedback loop. Expansion creates space. Space carries dark energy, and dark energy causes more expansion. This runaway process has enormous implications for the fate of the universe. In the distant future, far beyond anything humanity will ever witness, galaxies may drift so far apart that light from one cannot reach another. The universe will grow vast, cold, and isolated, with each galaxy becoming its own lonely island. The cosmos is not headed toward a grand cosmic collapse, but a long, slow stretching that continues for trillions of years. All because dark energy insists on turning the universe into the most aggressively expanding space you could imagine. The most perplexing part of dark energy is that no one knows what it actually is. It could be a fundamental property of the vacuum, a kind of built-in energy that comes from the restless quantum fields present everywhere. Or it could be something entirely new, a component of physics that has not yet been discovered. There is even the possibility it varies over time, changing intensity as the universe grows older. But whatever its nature, dark energy currently makes up the majority of the universe's total energy content. That means most of the universe is something we cannot see, cannot touch, and do not understand, but that still controls the cosmic storyline. One way scientists observe dark energy is by watching how galaxies cluster. Without dark energy, galaxies would gather more tightly over time, drawn together by gravity. But observations show the opposite trend. Large-scale structures are drifting apart faster than gravity alone can explain. Another method involves studying the faint glow left over from the universe's earliest moments. Subtle patterns in that glow act like fossils of ancient expansion, hinting at the presence of dark energy even billions of years ago. And in every measurement, every map, every simulation, the same conclusion emerges. Something is pushing on the universe with a gentle but unstoppable force. The idea that space itself has a built-in push is strange because it contradicts everyday experience. Nothing in your living room expands simply because it exists. Your books do not slowly drift apart over time. Your couch does not inch away from your coffee table. Thankfully, everyday objects are held together by forces far stronger than the expanding fabric of space. The influence of dark energy only becomes noticeable over enormous distances. Galaxies separated by millions of light years, clusters scattered across cosmic filaments. On the scale of planets and people, dark energy is silent. Yet on the grandest scales, its influence is undeniable. It is the reason we live in a universe that grows larger every second. It determines how galaxies evolve, how space transforms, and how the future will unfold. Even though it hides from detection and never reveals itself directly, dark energy sets the rhythm of cosmic expansion with unwavering persistence. If the universe were a story, dark energy would be the quiet narrator in the background, turning pages faster and faster while the characters scramble to keep up. It shapes the arc of everything, pushing the cosmos outward one moment at a time. We do not know what it is made of. We do not know why it exists. But we feel its influence in every widening stretch of space. The universe may be filled with mysteries, but dark energy stands as one of the most profound, a silent pressure that makes the cosmos grow faster than any rumor ever could, expanding reality itself with every passing heartbeat of time. If the sun had a personality, it would be the neighbor who leans over the fence every single day to talk, wave, share the weather, and occasionally toss a few energetic particles into your backyard for emphasis. Our star is not quiet. It never has been. In fact, the sun never stops exhaling even though it has no lungs. That constant outflow is the solar wind, a stream of charged particles racing outward in all directions, filling the solar system like an invisible hurricane that never ends. Earth, along with every other planet, moon, comet, and asteroid, is caught in its breath every moment of every day. To understand the solar wind, you first have to imagine the sun not as a serene glowing sphere, but as an enormous roiling cauldron of plasma, hot enough, bright enough, and chaotic enough to make any earthly furnace look timid. Deep inside, nuclear reactions fuse tiny particles into larger ones, releasing unimaginable amounts of energy. All that heat churns upward, stirring the outer layers into a chaotic dance. The sun's surface looks calm from far away, but up close it is a writhing ocean of rising bubbles, collapsing arcs, twisting magnetic fields, and explosive eruptions. In that turbulent soup, electrons and protons are not politely attached to atoms. They roam freely, forming a charged sea that constantly shifts and reshapes itself. Out of this dynamic surface emerges the solar wind, created because the sun's outer atmosphere, called the corona, is unbelievably hot. So hot, in fact, that particles there move fast enough to escape the sun's gravity entirely. Imagine boiling water so hot that droplets shoot off into space instead of falling back into the pot. The corona works the same way, just with temperatures in the millions of degrees. These particles fly outward, not in neat lines, but in swirling, chaotic streams propelled by both heat and magnetic forces. Despite their incredible journey, the particles that make up the solar wind are astonishingly spread out. A cubic meter near Earth might contain only a handful of them, nothing you would ever notice with your senses. But because they move so fast and fill such an enormous region, their effect is powerful. They shape the magnetic environments around planets, carve out enormous bubbles in space, and influence everything from comet tails to high-energy storms that dance near Earth's poles. The solar wind also interacts with the sun's magnetic field, which stretches outward into space like an enormous, twisting, spiraling structure. As the sun rotates, its magnetic field becomes wound up into a giant spiral pattern called the Parker spiral. This spiraling field lines the solar system like invisible threads, guiding and shaping the flow of charged particles. The solar wind does not simply drift outward, it rides along these magnetic highways, twisting and bending through interplanetary space in patterns that shift as the sun's magnetic cycle evolves. As the solar wind travels outward, it creates a vast bubble of influence around our entire solar system, known as the heliosphere. This bubble is enormous, so large that light itself takes years to cross it. Inside this protective region, the solar wind pushes back incoming particles from the galaxy, acting like a shield against some forms of high-energy radiation. Far at the outer edges, the wind eventually slows and merges with the thin material between stars. Spacecraft like Voyager 1 and Voyager 2 have crossed this boundary, sensing the subtle shift from the solar wind's domain to the broader ocean of interstellar space. It is like stepping from a gentle river into a vast open sea. Closer to home, the solar wind dances constantly with Earth's magnetic field. Our planet has its own protective bubble, the magnetosphere, that deflects most of the charged particles streaming from the sun. Instead of hitting us head-on, the solar wind flows around the magnetosphere, like water around a rock in a fast-moving river. But not all particles stay away. Some get captured, spiraling along magnetic field lines and plunging into the atmosphere near the poles. When they collide with atoms high above Earth, they create shimmering lights known as auroras. These glowing curtains of green, red, and purple paint the sky with the silent signature of the solar wind's visit. The solar wind is not steady. It changes with the sun's moods, swelling during periods of high activity and calming during quieter times. Solar flares and coronal mass ejections can blast enormous bursts of particles outward, intensifying the solar wind and sending shock waves across the solar system. These storms can disturb Earth's magnetic field, disrupting satellites, power grids, communication systems, and the delicate instruments that orbit our planet. Even though we cannot see or feel the solar wind directly, it affects our technology in ways we only began to fully understand in the modern era. Despite its disruptions, the solar wind is not an enemy. It is a reminder that the sun is alive with movement and energy. It is the signature of a star that refuses to sit still, constantly shaping the environment around it with invisible streams that stretch billions of kilometers. Without it, comets would not grow luminous tails. The heliosphere would not protect us from some harmful cosmic radiation. And Earth's skies would never glow with auroras that inspire awe in every generation fortunate enough to see them. The solar wind is the sun's breath, endless, powerful, and woven into the fabric of our solar system. Even without lungs, our star never stops exhaling, filling space with a stream of particles that whisper the story of its turbulent heart. If you could zoom out far enough from the universe to see its grand design, not just the stars, not just the galaxies, but the subtle threads that tie everything together, you would witness a stunning truth about the cosmos. It is absolutely obsessed with filaments. Thin, glowing strands of plasma weave through galaxies like electrical vines, twisting and stretching across light years of space. They bend, they branch, they pulse with energy, and they look uncannily like noodles. The universe apparently loves cosmic spaghetti, and it has been cooking a batch for billions of years. Plasma is not your ordinary state of matter. It is not solid, not liquid, not even the calm, predictable gas we breathe. Plasma is gas that has gotten so energized that its atoms split apart into charged particles, electrons and ions, moving freely in a chaotic, electrically conductive soup. Most of the visible universe is made of plasma, from the glowing body of the sun to the swirling matter inside galaxies. But the really strange part is how often plasma organizes itself into long, thin filaments that stretch across enormous cosmic distances, almost as if the universe prefers drawing lines more than it likes coloring in shapes. These plasma filaments form in places where magnetic fields thread through gas and dust, creating channels that matter follows like invisible rails. When charged particles encounter magnetic fields, they spiral and twist along the lines, and as they do, they begin to shape those fields in return. The result is a delicate tug-of-war between electric currents and magnetic forces, a cosmic braid that stretches through space. Even though the particles inside the filament move wildly, the filament itself often stays coherent for astonishing lengths of time, like a rope made of lightning that refuses to fray. Some filaments are found near galaxies where supermassive objects throw tantrums energetic enough to sculpt the surrounding material. At the centers of many galaxies, jets of high-speed particles erupt from spinning giants, huge spinning bodies that unleash streams of plasma into space. These jets eventually slow, twist, and break apart, forming threads that curl around the galaxy like strands of glowing thread. Other filaments are created by shock waves from ancient events, where powerful bursts of energy race outward and drag plasma along with them. Over time, these shock waves stretch, cool, and refine themselves into narrow, finger-like structures. One of the most breathtaking examples of plasma filaments appears in galaxy clusters. These clusters, collections of hundreds or thousands of galaxies, are surrounded by vast clouds of hot ionized gas. Within that gas, thin currents of plasma form delicate threads that link galaxies together in enormous webs. These filaments are not decorative. They act as highways for energy and matter. Hot plasma flows along them, carrying heat from one region to another. Charged particles race through them like cosmic traffic, and magnetic fields strengthen and stabilize them, giving them a longevity that defies intuition. Even more striking, some filaments glow. When energetic particles move along magnetic field lines, they can emit light visible in radio waves, infrared, or even X-rays. Observatories capable of detecting these wavelengths have revealed long, luminous lines stretching out from galaxies, some as thin as a few dozen light-years across, but extending up to tens of thousands of light years in length. Imagine a cosmic light bulb secretly connected by glowing wires, except the wiring stretches farther than the distance between many stars. These filaments do not just passively exist. They play an active role in shaping galaxies. They can funnel material toward the center of a galaxy, feeding the hungry supermassive objects that lurk there. They can channel heat away from dense pockets of gas, affecting when and where stars form. They can stabilize massive clouds of plasma, keeping them from collapsing too quickly. And in some cases, they act like energy rivers, distributing power across regions of space that would otherwise cool and fade. What makes plasma filaments especially mesmerizing is how they appear at every scale. In our own galaxy, delicate filaments snake through the glowing clouds near star-forming regions. They stretch across nebulae like pale threads pulled tight by invisible hands. At larger scales, they sprawl between entire galaxies, connecting them into clusters and superclusters. And at the grandest scale of all, the scale of the cosmic web, gigantic filaments composed of dark matter and rarefied gas form the backbone of the universe. Plasma collects along those grand filaments, creating glowing channels that trace the shape of existence itself. Plasma filaments also carry electric currents, sometimes incredibly strong ones. These currents can influence the shape and strength of magnetic fields, which in turn guide the plasma and reshape the filament. The interaction is so intertwined that separating cause from effect becomes nearly impossible. The filament exists because of the magnetic field, which exists because of the filament, which exists because of the charged particles following it. It is a cosmic chicken and egg scenario with no clear beginning, only a mesmerizing ongoing dance. Yet for all their complexity, filaments are incredibly fragile. A slight shift in energy can cause them to bend, kink, or break. They respond dramatically to disturbances, shock waves, bursts of radiation, gravitational nudges from passing objects. They twist into corkscrews, ripple like banners in the wind, or collapse into puffy clouds. And then, with time, they reform. The universe never lets them stay still for long, so the next time you think of space as a quiet, clean vacuum, imagine instead a galaxy full of glowing threads stretched across the darkness like strands of cosmic pasta. These filaments weave energy, guide matter, and trace the unseen skeleton of the universe. They are fragile and powerful, delicate and immense, chaotic and structured. And through them, the cosmos reveals one of its favorite creative impulses, a love of patterns, pathways, and, apparently, cosmic spaghetti. If space-time were a calm, perfectly still pond, then gravitational waves would be the ripples spreading across its surface, delicate, fleeting, and triggered by something dramatic splashing into the cosmic water. But the universe is not a calm pond. It is an enormous, ever-shifting, occasionally chaotic ocean where massive objects whirl, collide, merge, or explode with spectacular enthusiasm. Every time something huge rearranges itself in a hurry, two dense remnants spiraling together, a massive object collapsing, or an orbit suddenly tightening, the fabric of space-time quivers, sending ripples outward in every direction. These ripples travel vast distances, stretching and squeezing reality itself as they pass. Gravitational waves are basically the universe's version of someone knocking on the door to say hello, except their knocks travel for billions of years, through galaxies and voids, whispering stories of violent cosmic events. To understand gravitational waves, you first need to imagine space-time not as an abstract concept, but as something with texture, an elastic, responsive medium that can bend under weight. Massive objects such as stars and planets deform space-time just by existing. They sink into it, curving the geometry around them the way a bowling ball sags a rubber sheet. Smaller objects follow these curves, not because they are being pulled by invisible strings, but because space-time itself guides their motion. This is the essence of gravity. And when massive objects move suddenly or violently, they do not just sit quietly in their little dents. They tug and twist the surrounding space-time, sending out waves that ripple away like vibrations in a cosmic fabric. The most common source of these waves comes from pairs of compact objects, neutron stars, and extremely dense remnants left behind after massive stars collapse. These stellar corpses often end up in binary systems, orbiting each other at breathtaking speeds. Over time, they spiral inward, losing energy to gravitational waves. As they get closer, their orbit tightens, their speed increases, and the waves they send out grow stronger and faster. In their final moments, they whip around each other hundreds of times per second before colliding in a spectacular burst of energy that would outshine entire galaxies if we could see it directly. Instead of glowing brightly, these collisions shake the structure of space-time so powerfully that the resulting waves travel across the universe for eons before faint traces finally reach detectors on Earth. Even more dramatic are mergers involving the most extreme objects in the universe, black holes. Black holes are regions where space-time is curved so intensely that nothing, not even light, can escape. When two black holes orbit each other, they twist space-time into spirals, creating waves that radiate outward like cosmic drumbeats. The final moments of a black hole merger are unimaginably violent, yet silent. No light escapes the chaos. But the gravitational waves carry the imprint of that event, a whisper of a collision that happened far, far away. Detecting these waves is one of the most astonishing achievements in scientific history. They are incredibly faint by the time they reach Earth, so faint they distort distances by less than the width of a proton. To catch them, massive observatories stretch long arms of vacuum-sealed tubes across desert plains and forested valleys. Lasers bounce between mirrors inside these arms, measuring tiny changes in length as gravitational waves pass. When a wave arrives, the laser beams shift ever so slightly, tugged by the stretching and compressing of space-time. The first confirmed detection was a moment so monumental that it echoed through the scientific world like a cosmic announcement. We had just listened to the universe in a way that was impossible before. The wave itself had come from two black holes merging more than 1 billion years ago, long before Earth hosted anything more complicated than microscopic life. By the time that ripple washed over our planet, humanity had evolved language, technology, and curiosity strong enough to build instruments capable of hearing that ancient cosmic knock. Gravitational waves do more than signal collisions. They carry detailed information about the objects that created them. Their frequency and shape reveal the size of the colliding bodies, their masses, their distance, and their final moments before merging. The waves can also hint at how fast black holes spin, how dense neutron stars are, and whether their internal matter behaves in ways we have never observed in any laboratory. Each wave is a message written not in light, but in the shifting of space-time itself, a kind of cosmic Morse code that we are only beginning to decipher. As more detectors are built and refined, scientists expect to hear a wider range of events. Some waves may come from distant supernovae, massive explosions that send shock waves through space-time. Others may echo from early epochs of the universe, carrying clues about its first moments. There may even be signals from exotic objects or processes we have never imagined. The universe has been ringing with gravitational waves since its birth, and only now are we learning how to listen. One of the most delightful aspects of these waves is that they give us a new sense of the universe. Before, we saw the cosmos through light, visible light, radio waves, infrared, X-rays, gamma rays. These windows let us observe brightness, heat, color, and energy. But gravitational waves add something new. They let us feel the universe's motions. They let us detect the squeezing and stretching of space itself. It is like going from watching a silent movie to hearing the soundtrack for the first time. So when a gravitational wave sweeps over Earth, it is not just a passing ripple. It is a greeting from some distant part of the cosmos, a knock on the door from something massive and spectacular happening far away. The universe has always been busy, always in motion, always reshaping itself. Now, with gravitational waves, it finally has a way to say hello. If the universe ever threw a party, and let us be honest, the beginning of everything is exactly the kind of event that deserves confetti. It left behind one of the most enduring souvenirs imaginable. Spread across the entire sky, in every direction you look, is a soft, ancient glow, a whisper of light so old and so stretched out that it hums in the microwave range instead of shining brightly. This faint radiation is the cosmic microwave background, the after-party light from the universe's birth. It is the cosmic equivalent of leftover glow sticks still shining long after everyone else has gone home. To understand what this glow really is, you have to rewind the universe's story all the way back to when everything existed in a dense, blisteringly hot state. In those first moments, space was not full of stars or galaxies or even atoms. It was a chaotic, tightly packed sea of particles, ricocheting off one another at ferocious speeds. Photons, the particles of light, were there too, but they could not get very far. They constantly collided with free electrons and protons, bouncing around like panicked fireflies in a crowded room. The universe was so dense and so energetic that light had no freedom to move. It was trapped, scattered in every direction, locked in a fog so bright and intense that it would have made the surface of the sun look dim. But the universe did not stay that way. It expanded. It cooled. It stretched the way rising bread dough pushes outward, but on a scale so enormous that numbers fail to capture it. As the universe cooled, a remarkable transformation occurred. Electrons settled down and joined with protons, forming neutral atoms. Suddenly, light was no longer trapped. Photons that had been endlessly bouncing finally found the universe transparent. They traveled outward freely, carrying with them the signature of the precise moment that everything became clear. These photons have been traveling ever since, passing through billions of light years of expanding space. They come from everywhere because they were emitted everywhere. Every corner of the cosmos carries its own contribution to that ancient glow. As space expanded, the light stretched with it, cooling and redshifting from blinding brightness to the soft microwaves we observe today. Now, more than 13 billion years later, those photons form a uniform, gentle background that fills all of space, like a fading echo of the universe's earliest light. When scientists first discovered this glow in the 1960s, they mistook it for interference. Pigeons nesting in the antenna, faulty equipment, cosmic static. It took time to realize they had stumbled upon one of the most important discoveries in modern science, a direct snapshot of the early universe. Once they understood what it was, cosmology changed forever. The cosmic microwave background became the ultimate baby picture of the cosmos, a portrait taken when the universe was only a few 100,000 years old, long before stars existed, long before galaxies spun into being. Although the cosmic microwave background looks uniform at first glance, it is not perfectly smooth. Precise measurements reveal tiny temperature differences, minuscule variations, just fractions of a degree, that map the earliest imbalances in the young universe. These differences are the fingerprints of structure. Where the glow is slightly warmer, matter was a little denser. Where it is slightly cooler, matter was more spread out. Over billions of years, those tiny fluctuations became the cosmic scaffolding from which galaxies, clusters, and cosmic filaments eventually grew. In other words, the unevenness in this faint radiation seeded the large-scale architecture of everything we see today. Modern instruments have mapped the cosmic microwave background with astonishing detail. Satellites orbiting Earth have spent years measuring every direction, every fluctuation, every tiny deviation from uniformity. The result is a map that looks like a colorful speckled oval, a cosmic heat map encoding the early universe's blueprint. It contains information about the age of the universe, the density of matter, the amount of dark energy, and the overall shape of space-time. It is remarkable that the oldest light in the universe, stretched into faint microwaves, holds the key to so many of the cosmos's deepest secrets. One of the most intriguing aspects of the cosmic microwave background is its near-perfect uniformity. No matter which direction you look, the glow is almost exactly the same. This suggests that the early universe was remarkably even, at least on large scales. Yet the tiny imperfections are just enough to explain how structure formed. It is a delicate balance, uniform enough to make sense, varied enough to build everything. If the early cosmos had been too smooth, galaxies could never have formed. If it had been too clumpy, everything would have collapsed into black holes long before complexity emerged. The cosmic microwave background shows us that the universe began with the perfect recipe for future creativity. Another interesting revelation from this ancient glow is that it gives us a cosmic reference frame. Because the universe expands uniformly, the cosmic microwave background appears evenly distributed, unless you are moving. Our entire solar system, for example, is drifting through space at enormous speed, and the cosmic microwave background reveals that motion. The glow is slightly warmer in the direction we are moving, and slightly cooler behind us, creating a subtle dipole pattern. It is the ultimate speedometer for cosmic travel. And perhaps the most magical thing about the cosmic microwave background is that it is still here. It fills every corner of space, bathing galaxies, planets, and interstellar voids in its soft relic light. You can detect it with the right kind of antenna. It passes through you right now as you read or listen to these words, a silent, ancient whisper of the moment the universe first became transparent. The cosmic microwave background is not bright, not loud, and not obvious. Yet it is one of the greatest storytellers of all time. In its faint glow lies the memory of creation, the first moments of order emerging from chaos, the instant the cosmos opened its eyes. It is the after-party light of the universe's birth, still shining, still swelling with meaning, still painting the sky with the gentle echo of everything beginning. If you ever thought galaxies were the main characters of the universe, and everything between them was just empty stage space, The cosmos has news for you. It hates leaving blank areas. Even the vast stretches between galaxies, regions so enormous and so dark they make interstellar space seem cozy, are not truly empty. Instead, they're filled with an extremely thin, extremely faint spread of matter, known as the intergalactic medium. It is the universe's ultimate background texture, the faintest whisper of substance in places where you would expect absolutely nothing. Space cannot resist adding filler even in the biggest gaps, and this filler, delicate though it is, plays a much bigger role in shaping cosmic history than its ghost-like appearance suggests. To grasp the intergalactic medium, you must first stretch your imagination to the scale of the cosmic web. Galaxies are not scattered randomly. They form along enormous filaments, long threads that create a three-dimensional lattice. Between these filaments lie gigantic voids, empty-looking regions that span hundreds of millions of light years. These voids are so large that you could toss entire galaxy clusters into them, and they would still look lonely. However, despite the apparent emptiness, the intergalactic medium permeates all of this space, filling the gaps with matter so spread out that it makes the best vacuum you can create on Earth seem like a dense fog. The primary ingredient of the intergalactic medium is ionized hydrogen, particles stripped of their electrons by powerful radiation that swept through the cosmos long ago. These particles drift freely through space, rarely interacting with anything. A cubic meter in a void might contain just a handful of atoms. A cubic meter in a filament might contain a few more, but still nothing close to the densities inside galaxies. Yet, when stretched across unimaginable distances, even a small number becomes meaningful. A few atoms per cubic meter, multiplied across billions of cubic light years, create a reservoir of matter that outweighs all the stars in the universe combined. The intergalactic medium has not always been in its current state. In the early universe, matter was packed far more tightly, hot and eager to collapse into new structures. As the cosmos expanded, matter thinned out. Clumps formed, creating galaxies and clusters, but between them the leftover material stretched thinner and thinner. Much of that material was heated by the first generations of shining objects. Energetic light from early stars and galaxies streamed outward, stripping electrons from hydrogen and leaving behind ionized plasma that now fills the cosmic voids. What remains today is a patchwork of temperatures and densities, a faint, warm glow of particles whose average motion would barely register on atomic scales, yet whose presence has shaped the evolution of galaxies for billions of years. Despite its subtlety, the intergalactic medium plays the role of cosmic traffic control. It regulates the flow of materials that galaxies need to grow. When a galaxy forms stars, it draws in fresh gas from the intergalactic medium like a plant drawing water from soil. Streams of gas slide along the cosmic filaments, channeled neatly by gravity, falling into galaxies in slow, continuous rivers. These cold streams provide the raw material for new stars and help determine how galaxies evolve over time. Without the intergalactic medium feeding them, galaxies would quickly burn through their internal supplies and fade long before they could assemble their sprawling collections of stars. But the intergalactic medium is not a one-way resource. It is also shaped and enriched by galaxies. When stars explode, they fling heavy elements, carbon, oxygen, iron, into surrounding space. Intense winds from star-forming regions blow bubbles in the intergalactic medium, pushing material outward. Jets from active galactic centers blast high-speed streams that heat the faint gas even farther away. Over billions of years, galaxies and intergalactic matter have danced in a cycle of giving and taking, feeding and shaping each other in a vast exchange that spans cosmic distances. Even though the medium is incredibly diffuse, it becomes a canvas on which galaxies leave their fingerprints. One of the most remarkable ways scientists study the intergalactic medium is by examining the light from distant bright objects such as quasars. As that light travels billions of light years toward Earth, it passes through countless pockets of intergalactic gas. Each pocket absorbs very specific wavelengths, leaving small notches, tiny bite marks, in the spectrum of the quasar's light. By studying these bite marks, researchers map the structure, temperature, and composition of matter spread across cosmic scales. These observations reveal a universe threaded with gas, forming long rivers and bridges between galaxies. It is almost poetic. The faintest matter in existence becomes visible only when a beam of ancient light passes through it, highlighting it like dust in a sunbeam. The intergalactic medium also influences the speed at which galaxies move and the overall structure of galaxy clusters. Even though the medium is thin, its total mass contributes to the gravitational landscape. Entire clusters of galaxies sit immersed in this faint ocean, their motions subtly guided by its invisible hand. It provides resistance to high-speed jets, it absorbs radiation, and it even influences how cosmic shock waves spread. Over time, it acts as a stabilizing agent, smoothing out irregularities and supporting the large-scale structure of the universe like a quiet scaffolding. It is astonishing to think that the most empty regions of the universe still contain matter, matter that flows, heats, cools, mixes, and moves in patterns shaped by gravity and ancient radiation. Space, it seems, cannot bring itself to leave any region truly blank. Instead, it fills even the largest voids with whisper-fine traces of hydrogen, helium, and the occasional heavier element, drifting endlessly across billions of light years. So the next time you imagine galaxies drifting through empty darkness, remember this: the darkness is not empty. It is filled with the thinnest, faintest, most delicate fabric of matter you could possibly imagine. Matter that has quietly shaped the cosmos since the beginning, filling every gap because the universe simply refuses to leave anything truly empty. If you were to take a step back from everything we have explored, from the dust drifting between stars to the vast web binding galaxies together, and try to imagine the universe as a whole, you might be struck by a quiet kind of revelation. Space, which so often gets labeled as empty, is anything but. It is a stage where nothingness is an illusion, a backdrop that only looks blank because the actors are either invisible, tiny, scattered, or simply too subtle for the casual observer to notice. But underneath that quiet exterior, the universe is buzzing with activity so constant and so varied that calling it empty is like calling the ocean dry because you are only looking at it from an airplane window. The truth is that space is alive with processes that unfold on scales far beyond what humans experience. Each phenomenon we have explored contributes its own layer to the cosmic symphony. Interstellar dust, small though it is, roams between stars, carrying the seeds of future worlds. The gas between stars, faint though it feels, sculpts the grand shapes of galaxies. Invisible particles streak through space at unimaginable speeds, born from the universe's most extreme events. Quantum fields tremble and quiver, ensuring that no point in the cosmos ever truly rests. Virtual particles, timid and brief, flicker into existence and vanish again like tiny sparks. Dark matter forms the hidden scaffolding that gives galaxies their shape, while dark energy stretches everything outward in a long, slow, cosmic expansion. The solar wind races outward from our star in a constant breath. Plasma filaments weave bright threads through galaxies, channeling energy like glowing arteries. Gravitational waves ripple across space-time, carrying news from distant collisions. Ancient light whispers the universe's origin story, and the sprawling intergalactic medium fills even the largest voids with matter too sparse to see but too important to ignore. Piece by piece, each of these ingredients builds a portrait of a cosmos that is dynamic, restless, and astonishingly full. Space may look empty to our eyes, but that is because human senses evolved to survive on the scale of trees, rivers, and mountains, not on the scale of particles, plasma, or gravitational ripples. Our eyes are not tuned to invisible mass or trembling fields. Our hands cannot feel the flows of ionized gas drifting between galaxies. Our ears were not built to hear the faint hum of gravitational waves passing through the ground beneath us. Space seems empty only because we humans are hilariously underqualified to detect most of what the universe is actually doing. And yet the universe does not need to shout to make its presence known. Even with our limited tools and senses, we have learned to listen. Telescopes reveal dust glowing faintly in infrared light. Radio antennas catch whispers from neutral hydrogen drifting through galactic filaments. Orbital detectors register dim echoes from the early universe. Laser interferometers sense the slightest tremor of space-time. Particle experiments record the traces of high-energy visitors from distant catastrophes. Step by step, discovery by discovery, we have peeled back the layers of the cosmos and found that the void we once imagined is brimming with detail. The deeper we look, the more we realize that the universe is not just full, it is structured, connected, and remarkably active. Dust shapes new stars. Gas organizes into spirals and nebulae. Black holes and neutron stars send ripples through space-time. Magnetic fields guide plasma through vast cosmic threads. Invisible matter shepherds galaxies across billions of years. Ancient light paints a memory of the universe's earliest clarity, and all of it together creates a cosmos that is far more intricate than any human myth or metaphor ever suspected. What makes this even more beautiful is that the richness of space is not limited to the spectacular. Yes, there are explosions, collisions, and colossal jets that launch particles across galaxies. But equally important are the gentle details, the slow drift of atoms across light years, the delicate pulse of fields just above the level of nothingness, the quiet tug of unseen mass shaping the paths of worlds. Space is not vibrant because of its drama. It is vibrant because of its constant, multi-layered, overlapping motions. The universe never stops working, never stops shifting, never stops telling its story through the faintest of interactions. And perhaps the most humbling realization is that all of this is happening right now, while planets spin, while stars shine, while galaxies rotate. The universe hums with background activity that will continue long after we are gone. Light from ancient events still moves through us. Particles from distant catastrophes still strike our atmosphere. Waves from ancient collisions still pass quietly through Earth. Fields still vibrate beneath every atom. Nothing is motionless. Nothing is truly empty. Space, for all its darkness and silence, is not a void. It is a grand mosaic of energies and materials, woven across scales so vast and subtle that our definitions of emptiness simply do not apply. The universe may appear quiet, but beneath that calm surface, it thrums with ceaseless activity. Interactions so small we cannot feel them, forces so large we cannot grasp them, and processes so ancient we can barely describe them. So the next time you look up at the night sky and see a dark patch between the stars, do not be fooled. That darkness is full of more stories than we can count. Stories written in dust and gas, in particles and waves, in fields and filaments and forces that quietly shape the cosmos. The universe is far too busy to ever be truly empty, even if it pretends otherwise.